So today we're covering two topics, variational autoencoders, VAEs, and generative adversarial networks, or GANs. It's the final day of the week, so this is like a little bit of a fun day. We get to like build something that like does something quite interesting. It's not quite as important to like say the material for next week, and it's not like a prerequisite for it, and that we move on to like LLMs. But I think this contains like a lot of useful material, sort of like get your hands a bit more dirty with like a real engineering kind of task with something that's like a bit difficult to train. You got to like wiggle a bit and try different things. You'll be building up a specification of a model similar to like the blueprints described on day 2. You'll be training and sweeping over it and have it like wiggle the hyperparameters a bit to make it train nice as we did on day 3. And we have to be careful with like how gradients flow back through the model, because GAN's a bit of a weird model, as we'll see, which hopefully harks back a bit to what we saw on day 4. So first off, an autoencoder is basically a method of taking a high-dimensional space, compressing it down, and then uncompressing it back up again. The goal of the autoencoder is to just be the identity function. And normally, if the model doesn't have a bottleneck in the middle, be the identity function is easy. The middle part just like learns the identity matrix, doesn't do anything interesting. The hard part here is because this middle part is like a low-dimensional space, the model has to essentially milk out like the important bits of the data and the input, and then like faithfully reconstruct it from that compressed representation. The idea here is that we're going to be using a convolutional neural network here that learns like whatever useful high-level features of the image there are, like the only useful bits, and then what's called a transposed convolution, which is kind of like an opposite convolution, maps from a smaller image back up to a bigger image again. Now, ideally, you can use this thing for generation by, once the model's trained, the latent vector in the middle is like some sort of like useful, rich representation of whatever data set you've trained on. And then you can feed through random noise here, and it like generates new images on the output. That's like sort of like the high-level idea. The problem is that like, as they currently are, autoencoders are like not really good for this sort of thing. So here we've trained an autoencoder on the dataset MNIST, and then we take a two-dimensional subspace of the latent space in the middle, and we sort of sweep over it. And so then we're sort of interpolating between 2 points in latent space, and you kind of get garbage. It's like not very good. Why is this not very good? So the problem is that the autoencoder tends to memorize a bit. If it learns to like always send 7s to this region of space and always send 2s to this region of space, and they're like very close, but it can easily distinguish them, it's kind of just memorizing. If different numbers get sent to like different regions in space, and there's never any overlap in the middle, that is, it's never seen a latent vector between 7 and 2 during training, we wouldn't expect that when we try to reconstruct it, we get anything meaningful. And this is in fact what you get. When you try to like run the decoder on halfway between 7 and 2, you kind of get garbage. It doesn't do very well. So to tweak this, we construct what's called a variational autoencoder. Autoencoders try and learn mappings to latent space. Variational autoencoders learn distributions in latent space. So here's the fix. When we feed in, again we'll stick with MNIST, when we feed in numbers, the model learns like a distribution in latent space of like where 7s live, a distribution latent space of where 2s live. This means that like not everything gets mapped to a single spot, like the model has to like make a more rich use of the latent space, it like fills up the entire space. And it also means that there's going to be like overlap between these 2 regions. So something that lives kind of halfway between 7 and 2 has to kind of look like a bit of a 7 and look like a bit of a 2. In practice, what this looks like is that the model learns a mean and a standard deviation, which defines like a Gaussian. And then for the decoder, we sample things from that Gaussian. So there's like also a bit of noise in this process, and the noise helps with regularization. The model's going to learn not just how to map from 7, but how to map from things that are near 7, and things that are near 7 in latent space hopefully look like 7s according to the decoder. So it's going to be like robust to a bit of noise, which helps with generalization. So if we do this for a variational autoencoder, we can sort of conceptualize halfway between 7 and 2 as it's something in the MNIST data set that would be equally likely to be classified as a 7 or a 2. And if you interpolate between these, so the encoder maps a 7 here and it maps a 2 here, we interpolate and decode, you get something that like actually looks reasonably halfway between a 2 and a 7. I would call that about halfway between the two. It's got properties of both. It's kind of got a big strokey part here and a little flicky tail there. I'd say this is like reasonably doing well at interpolating between the latent space. The latent space is now like meaningful, and we can sweep through it, and that is like a meaningful thing to do. Architectural-wise, the autoencoder is above, the variational autoencoder is below. So the encoder learns mean and standard deviation. We then sample a latent vector from that, and then we decode to get the full image. There's also an additional loss term that we penalize the mean and the standard div to not drift too far from a standard zero mean unit variance Gaussian. And the reason we do that is because if we didn't have this penalty, the encoder would just learn to put the mean for 7 way over here and the mean for 2 way over here and have the standard deviation really, really low. So it's just like all the 7s are on this dot here and all the 2s on this dot over here, and we're basically back to the same problem as we were before. We want there to be overlap. So the decoder has to learn to be able to deal with these things and have like the entire latent space be used up. Otherwise, we're kind of back to where we started. Now, the other tricky caveat here, actually maybe it's another good time to pause for questions because I've said a lot of words. Yeah.
So what's the purpose of this network? Like, is the end goal we give it an image and we get a classification?
Well, this will only do the identity function, but the end goal is that after training, you can throw out the encoder, feed in random noise into latent space, and like generate new numbers.
So both the VAEs and GANs we're looking at are image generators.
Yeah, so the only reason we have the encoder is sort of to help train the decoder, but the decoder is the part we're actually interested in at the end of the day. Like, all this thing does is do the identity function, and that's not very interesting. I can already do that identity function, but it's learning to reconstruct from a compressed space that's the interesting part. Yeah.
Can you use a VAE on text tokens?
Ooh. I mean, in a sense, transformers kind of do this in that the embedding matrix maps from tokens to latent space, and then like interpolating between latent space is like a meaningful thing. Maybe we'll like come back to this when we do like transformers, but like, yeah, weakly yes, and in some sense transformers kind of do this, already have the rich latent space in the middle. Yeah.
What the mean and the standard deviation, what are they the mean and standard deviation of?
They're going to be, do I have a picture for this? Let's jump back. They're going to be, assuming let's say the latent space is 2-dimensional, then 7s get mapped to a mean of here and a standard deviation of roughly so big, and 2s get mapped to a distribution with mean here and standard deviation so big.
So the encoder outputs a mean and standard deviation, but the decoder uses those and injects some random noise to actually sample from that. So the decoder is non-deterministic, unlike a normal autoencoder.
I would say mild caveat, the decoder is deterministic, but we inject random noise into it. That's where the random noise comes from.
Is this saying map all of the 7s to latent space in such a way that you have the standard, you have a mean and a standard deviation, and then you have some penalty that makes that standard deviation be closer to 1?
Yeah, so like all the 7s map to some probability distribution, such that distribution is penalized to be not too far from a unit variate Gaussian. And also, if you try to reconstruct from those points, you get the same pictures of 7s back again. So the model's got like two competing goals. Like, if everything gets mapped to the same point in latent space, this penalty goes to 0, but now I can't tell 7s from 2s because my latent vectors are the same and reconstruction is terrible. If I push these distributions very far away from each other, then reconstruction's easier because it's easy to tell 2s from 7s. But now this penalty shoots up to infinity. So the model's got like two goals, like latent space has got to be like reasonably well used and things have to overlap, but also reconstruction has to do well. And so that means the model has to like use up the entire space, and interpolating between 7s and 2s happens to get you a somewhat reasonable image. Because the reconstruction loss, if I were to feed through a 7 or feed through a 2, this is like kind of close to both, if you measure like the pixel difference. Whereas if I feed through an 8, it'll probably get mapped to somewhere else, because the model wouldn't want to reconstruct an 8 like this, because this doesn't look like an 8. This is the kind of like higher level intuition. Cool. Anything else, or shall I move on? Last one.
Does the randomness mess up that property?
Oh yeah, there's a way we have to deal with that. Cool, I have a slide for that. So obviously, you want to backprop through the operation, sample a latent vector from mean and standard div. Yikes, I don't know how to backprop through that. So we have a dirty trick for that. And the trick is we always generate zero mean unit variance noise from like this is a little leaf node that we don't backprop through. And then I take that noise and I multiply by my standard div and I add the mean to it to get the latent vector z. So when I backprop through, I can backprop through all of these guys, but I don't backprop through this. It's just like noise that's injected. That's how we deal with it. So in essence, generating zero mean unit variant noise and then scaling it in this way is equivalent to sampling z from this distribution, but now the gradients can actually flow through and do something meaningful. So that's how we deal with the backprop. Cool. Any other, yep?
How do we achieve the trade-off between the two training objectives? Like they learn the trade-off by automatically, or like we have hyperparameters?
We have a hyperparameter. So the actual loss at the end of the day is like reconstruction plus alpha times KL divergence, and then you twiddle alpha. If alpha is really small, then the reconstruction is great, but now your latent space is garbage again because it just learns to put things far apart, and then when you interpolate, you get garbage. If alpha is really big, then the model just makes every distribution be the unit identity, and your latent space is like all numbers get mapped to the same place, and reconstruction is terrible. And then you just like wiggle alpha until like, I mean, what you care about at the end of the day, your only ground truth is inject random noise, get reasonable pitches out, or like sweep between 7 and 2 and get like things that look kind of like 7s and kind of like 2s. But yeah, you just have to like wiggle the hyperparameter and see what you get. Cool, yeah.
Another question is, how do we evaluate the goodness of our latent space? Because of course we are training with a reconstructive loss, but it's not the goal, right?
That's right.
Like the goal is to have a meaningful latent space.
Yeah, so during training, every now and again during the evaluation step, you just like shove some random noise into the latent and decode it and then look at it and go, oh yeah, that looks good.
So it is by hand?
Yeah, there's like, I mean, how do you automatically, I mean, it's like training a generative image model. What's your measure of like, yeah, this looks good to me? And it's kind of hard. I mean, GANs kind of have a way to deal with this. But by default, there's no real ground truth feedback other than like sweep over, just do like 10 training runs with like different hyperparameter trade-offs between this loss and that loss, and then just like look at it and see if the decoder does good or not. But yeah, we don't really have ground truth here. Yeah.
Can use maybe a classifier on the images and see like if it's recognizing the images as the correct.
GANs do this. We'll come to that when we talk about GANs.
Why can't you do that with VAEs?
I guess you could, but then you just kind of be reinventing GANs in a sense. I'll come back to this when we get to GANs. Yeah, last one.
So the goal would be that the latent space is like saturated in such a way that any sort of random noise you give it would map to like at least one of the distributions of like the
Yeah, would map to something that vaguely looks like an MNIST digit or whatever data set you trained on. Yeah. Cool. Okay, cool. That's variational autoencoders. Does the latent space look better? Yeah, it sure does. If you like take a two-dimensional slice of the latent space for VAEs and you sweep over it and you pump it through the decoder, yeah, these all look kind of like numbers. These are like 90. This is like, it's kind of like 8s in the middle. Then over here is 3s and over here is kind of 5s, kind of 6s. Like does a bit better. I'd say this is like something a bit more meaningful. VAEs and GANs are no longer state of the art. The current hot stuff for all the image generation models is what's called diffusion models, but there's kind of a relationship between them. For diffusion models, which we don't cover in Arena, basically the encoder is to take an image and like gradually add noise to it in stages, and the decoder tries to undo this process, so like remove the noise back out. So if I give you this photo here of the kind of garbled up cat, it's like not too hard for you to see the cat underneath. And you imagine to go from here to here is like maybe not too hard for a model to undo. And once you've trained all this, you take the decoder, you inject random noise, and it just like hallucinates the image it thought was noise to get there. And this like does like crazy well, as it turns out. I mean, as you already have seen. So most image generation stuff is diffusion. There's also a new thing hot off the press called transfusion, which I think is using some transformer to do this. I haven't read the paper myself, but it's a thing. Anyway, GANs are great, but they're no longer state of the art, but they're like a good engineering thing, and we can train them relatively fast, so that's why we do them. Cool, okie dokie. GANs. GANs were a really big thing when they came out in 2014. They were at the time the state of the art in image generation. And they're really annoying and pesky and unstable to train, as we're going to see. Like VAEs, many ideas from GANs have worked their way into other image models, like diffusion, although maybe less of a direct lineage as compared to VAEs, where there's like clear distinction between like encoder, decoder, and get like a latent space in the middle. So high-level picture of what a GAN does. GAN's got two parts, a discriminator and a generator. The job of the discriminator is to tell reality from fiction. You feed it images, and it says, yes, these ones are real, and no, these ones were fake. The goal of the generator is to generate images that fool the discriminator. So initially, the generator does like a bad job of generating fake pictures. The discriminator can clearly tell the difference, and the generator gets the discriminator's classifications as feedback to like do better at fooling it. And eventually, you let this cook for a while and train. And hopefully, if all does well, the generator can distinguish images so close to reality that the discriminator can no longer tell reality from fiction. So we're training two networks in parallel with like kind of almost opposite goals. My job is to tell things apart. Your job is to generate things that fool me. It ends up you have like a moving target because these two networks don't really have like a ground truth to compare against. They kind of train against each other like some evolutionary arms race, which means sometimes things can just like fall over. And this is what you'll be seeing today. Cool. Whoopsies. Okay, so here's like a high-level picture of the sort of like architectural blueprint for today. The discriminator is just a image classifier. It's just a big old CNN that takes an image and maps it down to a single scalar number, and that scalar number is the confidence of the model that this image is real. The generator is basically the same as the decoder for VAEs. It takes in a latent vector and maps it up to an image with like some sort of like convolution transpose thingy. How do we train these things? So we have a bunch of real images in a data set, and we have random noise. We feed the random noise into the generator, and it spits out, hot garbage at the start of training, but spits out things that are image shaped. We feed these things to the discriminator, but we don't tell it which ones are real and which ones are fake. And the discriminator is trained with standard cross-entropy loss for classification, maximize the probability if the input was a real image, and minimize the probability if the input was a fake image. That's like the training objective for the discriminator. So it wants to maximize the log probability of real stuff and minimize the log probability of fake stuff, or in this case, maximize log of 1 minus the probability according to fake things. So this is the objective of the discriminator. And the objective of the generator is to maximize the likelihood the discriminator says if I feed it a fake image. Now, this optimizer doesn't have access to these weights, because otherwise this guy could just muddle his weights up. If you're trying to fool me with images, the easiest way to do that is probably take a brick to my skull, and then I can't classify things anymore, so you can't do that. And this optimizer doesn't have access to that, because the easiest way for the discriminator to tell real from fiction is I just break your hand and then you can't draw images anymore. So we're not allowed to do that. So this guy is trained to distinguish things, this guy is trained to generate things, and they kind of fight each other during training. That's like high-level picture of a GAN. People want to ask me questions? Yeah?
What stops the generator from could it somehow learn one of the real samples and then just whatever input it gets to be able to generate that?
I guess if you have a small enough data set, and if the generator gets enough feedback, the generator only gets feedback of how well the discriminator is doing, but maybe over long enough, the generator just learns, let's say, what the real images are. If you have way more data than the size of the generator, it can't possibly memorize all the images. But if your data set is really small, yeah, the generator could just spit out the images in the data set, and then the discriminator is hopelessly screwed.
Could it just only generate one image again and again? The one that's found seems to do
Okay, suppose it only ever generates the same image. The discriminator then learns every time I see that image, it's fake. And then you get the big gradient stick, and the generator goes, oh no, I'll have to try to do something else.
So that means it has to try and learn something like the distribution of...
Exactly, that's the goal. So really, these images are sampled from like, I don't know, God's Platonic distribution of real images, and the generator is trying to learn that, not trying to generate whatever happened to be in the data set. Also, this guy doesn't directly have access to real images. Yeah.
So is this sort of like RL, but you're also updating the reward function every time?
There's some similarities here to reinforcement learning. I would call this, I mean, this is like adversarial training, that you've got two things competing with each other. And in some sense, you could consider a reward function for this guy as like how good you are telling reality from fiction, and this guy's reward is how good you are at fooling this. But they don't get a scalar feedback, they get like an actual loss with a gradient feedback. So I would not classify this as reinforcement learning, though there are some like similarities.
I was thinking of the discriminator like as the reward model. But if it's not helpful.
Well, this guy gets feedback directly from here. It's like the loss of this guy is the log of the probability that the discriminator assigned to fake stuff that I generated, and I can like backprop directly through it. So while the gradients for the generator flow through the discriminator, when I compute this, I like detach this part. So I'm not allowed backprop through the generator to like wiggle the discriminator weights directly, but the gradients flow through here to compute this guy. So it's a much more, trying to think of a good way to phrase this. It's like I have like white box access to your brain with like an MRI machine, but I can't wiggle things directly. I can just use that information to try and fool you, but I can't reach in there with my like probe and touch stuff, which is much more rich with RL. With RL, I just get outputs from you, but you are a black box that I can't see the insides of. Yeah?
Sorry if I missed that, but how is the discriminator trained?
The discriminator is trained, it feeds in real images and fake images, and it spits out labels, and we just train it like it's a classifier. Real image is 1, fake image is 0. This guy has to guess the label.
So they're getting trained at the same time?
They get trained at the same time, yes. Which means in practice, this guy gets a batch, that guy gets a batch, and you like step them one after the other. Yeah? Sometimes. Yeah.
I assume the problem is when the like skill levels get out of balance and like one gets really good and then the other.
Yeah, we'll talk about that in the next slide. Yeah. Okay.
I just wanted to clarify on the reinforcement learning question. The reason we just, so checking I understand, the reason we don't call it reinforcement learning isn't because of the setup, it's because of the mechanics of exactly how we do updates to the model.
Yeah, like if all this guy got his feedback as like, here are the images the discriminator got tricked by and here are the ones that it wouldn't, go work it out, this would be more of an RL framing. But here we actually backprop through this. You get a much more rich signal. Like implicitly in the gradients, the generator gets feedback of these are the directions in which would be more fooling towards the discriminator in like, you know, gradient space or whatever. All right, I'm going to move on. Okay, failure modes. First off, the loss curves just look completely bonkers because like the generator gets a bit better at distinguishing, and then the generator gets better at fooling, and then the discriminator gets better at distinguishing. Is like do. So these got to fight each other. So like one, your loss curves look kind of whack. Basically, as long as like one of them doesn't like spike to infinity on the other flat line, which basically means like the generator is always good at making fake stuff, or the discriminator is always good at distinguishing, and then learning kind of like stalls, that's fine. Like you want these things to be like roughly about the same value and roughly like wiggle up and down for a long period of time, because this tells you nothing about the actual performance of the model, right? Maybe the discriminator is like really stupid at telling reality from fiction. The generator always knows what's to generate, but it doesn't actually look like a real image. So like lots of ways in which this fails. So like the discriminator can quickly outpace the generator and get perfect at classifying, which means this term here, the probability the discriminator assigns to fake images goes to 0, and log of goes to 0 goes to minus infinity, and then like gradients blow up and training blows up, you get like nans or minus infs and the whole training run falls over. This happens all the time. Other things that can happen is these guys can like spin back and forth, but like no one really gets an advantage and they don't really learn anything. Or if the models are unbalanced, if like the generator is like too big and too clever, or the discriminator is too big and too clever, one outpaces the other and the other can like never really catch up. Fixes are like mostly hacks. Like whoever's in the lead, whoever is not in the lead, you like get him to do a few extra gradient steps to catch up. You can try use soft labels, so the labels are not 1 and 0, but like 0.1 and 0.9, which means you're training the discriminator to like never be like absolutely fully certain. This can like help to like mellow things out a bit, but also means training is slower. If you get a batch where you calculate losses like NaN or infinity, just like throw that batch out and try another batch again. And if you always get that, then like you're screwed, train starting again. Even when everything's working perfectly, a lot of this is like very finicky, and you just like run it and it crashes, and then you spin it up again with a different initialization of the random weights of the model, and then it does good. GANs are just like inherently, notoriously finicky things to train. That's just how they are. That kind of sucks. On the right-hand side is like state-of-the-art for GAN-based approaches, and this is the kind of Lovecraftian horrors that you will get today if you let it cook for, so this is like maybe after like 30 seconds, this is after like maybe 10 minutes, so if you let it cook for an hour or so, you get something. I mean, that's like a face if you squint, that's like pretty good. I don't know about that, but like, anyway, like not bad for something that we can like train on the spot. This is what like state-of-the-art image generation looked like circa like 2014, 2015. And this is what state-of-the-art looked like until we sort of switched to like diffusion models. So like you can actually do pretty well with GAN approaches. They're just like really difficult to train. Cool, that's all the things I had to talk about. So we'll do a few more questions, then we'll wrap up the talk for today. Yeah.
Can you clarify how the gradients flow between the discriminator and
Yeah, let me stare at this for a moment. Okay, so this guy wants to maximize the discriminator's classification of fake images. So the gradient path for here would have to be through the discriminator and then through the generator itself. So we have like noise comes in, generator generates stuff, discriminator classifies stuff, compute the loss, and that's like the gradient path for the generator.
Okay, and it can only modify the generator weights.
Yes. This loss term here can only modify these weights. This loss term here is a function of both taking the real images, get the discriminator to classify them, and take in the noise, generate some stuff, get the discriminator to classify them, and then this loss term here, the optimizer can only touch these weights here. So it's kind of weird, we got like two gradient paths here, and two separate things we're optimizing. This can only touch this, and this can only touch that. Does that answer your question?
Yes.
Great. Anyone else got any other questions? I'll walk back into frame. There we go. Yeah.
At one point I remember reading that the common wisdom is sort of shifted to like you actually want a really strong discriminator, and you don't need to worry as much if the generator is weaker.
This is news to me. I don't know that much about GANs. You could certainly try this during the day and just like make this bigger weights, like make it, this is like a CNN. You could just like make the kernels bigger and make the classifier bigger and see if that helps. Yeah.
Is there any way to tell just like plotting the loss or something, some metric during training if the training is doing okay without final images?
Basically, as long as the loss curves are both like still going and about the same size and both wiggling back and forth, this is like a good sign. Because like if the loss is changing, then the models are like learning something. But if the loss is like flatlined to 0 for the discriminator, then it's like I'm perfectly omniscient at classifying real from fiction, and I'll never learn anything ever again. And this is like usually bad. So like as long as the losses are like about the same order of magnitude and both wiggling, something is happening. I don't know if it's the right thing. And again, our only ground truth is during evaluation time, we inject some random noise into the generator and we look at the pictures we get, and if they look like Lovecraftian horrors of faces, then like cool, I guess that's about what we wanted. Yeah.
In terms of keeping one from getting too far ahead of the other, can you do something adaptive, like based on how well they've done on the last number of examples, like add more or less noise to the image before the discriminator sees it, or something along those lines?
There are lots of different hacky things one can try. They're mostly little hacky fixes, because in general this is like one step. But yeah, there's lots of things one can try. Like the naive thing to do is whoever's loss is lower, let him get another go. Whoever's loss is higher, let him have another go. But then sometimes you also get stuck in this way. Like this is just messy. Like,
It's worth mentioning that though GANs aren't state-of-the-art for image generation, there's still ongoing research with them, and they do still have their niche.
yeah. So.
I think it's still curious.
I couldn't answer off the top of my head, but I see patents still coming out of that.
Usually if you've got some like objective that you want to try fight against, a GAN approach, an adversarial approach can be a good way to start. I know again, it's more of an RL thing, but anyone see the OpenAI hide and seek things? Like the little blue guys want to hide from the red guys? That was trained with like a zero-sum reward model. So like blue is rewarded if it hides from red is rewarded if it sees blue, and you just let them fight each other for a while, and eventually they learn like really cool strategies. So this is like kind of that vibe. Whenever you've got like, I want some sort of proxy of metric or some sort of proxy of success to go up by two players fighting each other to learn a strategy that I couldn't dream of, adversarial might be an approach to try. All right, last question.
If the two losses are within the same order of magnitude, what could the possible like failure modes be there of them not learning what you want them to learn?
Maybe both the generator and the discriminator are like kind of stupid. So like the discriminator is not very good at telling reality from fiction. The generator is like not very good at generating fake-looking, realistic fake-looking images. And so they both kind of sit there and train, but they never actually improve. That could be like one potential failure mode, which like, I don't know, like,
It's just kind of like random.
yeah, maybe they get like stuck in some sort of local valley where the generator is stupid but can't learn how to make a better image for the discriminator, and the discriminator is stupid and never quite learns to distinguish the two, and they just kind of sit there and spin, but the images never start looking any better. That could be like one potential failure mode. Cool. All right, last one. Last one.
Can we initialize the discriminator from existing like image classification models like ResNet or
Oh, that's a good idea. I suspect if you tried this, the generator would just have like a really tough time dealing with like some omniscient godlike ResNet model classifying. Actually, I object. ResNet wasn't trained to distinguish reality from fiction. It was trained to classify things. Yeah. Maybe you take a ResNet, you lop off the final linear layer, you bolt on a new linear layer, and then you use that, and then you don't train these weights, you only train the last layer. That seems like I would try that, just see what happens. I have no idea what would happen. My initial gut reaction guess is the generator is just like up against this like godlike classifier and like really struggles. Or as Cole said, maybe apparently starting with a strong discriminator helps. I have no earthly idea. That's a fun thing, you should try it. Tell me what happens. All right, cool. I'm finished with the talk.